Hello everyone, this is Paula again, and today I have another supplemental video for you. This is just going over some basic integration techniques. So just like my other video, there is a lot of theory behind integration. I'm not going to be going over that today. I'm just going to be showing you basically how to integrate and how it can be applied to our class. So we have integration. Just like differentiation, we have a power rule here also. So for integration, our power rule can be used when we have, just like in differentiation, any kind of exponent. So the rule is that the integral of x to the power of n dx is x to the power of n plus 1 divided by n plus 1. So here, x is the variable we want to integrate, and that is shown by this dx here. So just like in differentiation, we look for the x out front, but here we're looking for the x inside the integral. So we see the x is our variable, n is just any number. So to do this integral, we simply just add 1 to the exponent. And when we add 1 to the exponent, we also put it in the denominator down here. So this can also be applied if there's any kind of coefficient out front here, like 3, say, if you had 3 times x to the n, that just comes with the whole expression and it would go in the numerator up here. So we will see some examples of that. I also forgot, you need to add a constant if you're doing indefinite integration. So if there is no bounds up here. If you have done integration before, you will know that. If not, don't worry about it too much. We're not going to be using that much here. What we will be using in this course most often is called, I guess, definite integration, or integration with limits is usually what it's called. So this is when you're integrating from some start value to some end value. So if we're doing that of x to the n dx, that is simply just our same expression as before. So x to the power of n plus 1 over n plus 1. But this time it is evaluated from a to b. So all that means is we're basically just plugging in these values. So you can think of b as the final value and a as the initial value. And I always think of that because usually in physics, you're subtracting the final from the initial. So that usually helps me remember which order to do this in. So we just sub these values in for x. So first we have b to the power of n plus 1 over n plus 1 minus a to the power of n plus 1 divided by n plus 1. So that is how you evaluate a defined integral between two bounds. And you don't need a plus c at the end. You don't need to worry about that. So this is all kind of complicated when you just have symbols there. Let's do some practice. So let's find the integral of 3x squared dx. Okay, so taking a look, we have x as a variable here since we look at our dx there. So performing this integral, we will use our power rule. So we have the 3 that just comes with the variable there. So we have 3x to the power of 2 plus 1 divided by 2 plus 1. And we can just simplify that. So 3x, 2 plus 1 is 3. And on the bottom, same thing, 2 plus 1 is 3. 3 divided by 3 cancels out, so we just get x cubed, and we will do plus c since this is an indefinite integral. So we're not going to be seeing too much of those. Let's move on to some defined integrals. So if we want to do the same thing, integrate the same expression, except from 1 to 3 of 3x squared dx. Well, we've already found what the integral of 3x squared dx is, so let's just plug that in there. It is x cubed, and we want to evaluate that from 1 to 3. So we just plug in 3 for x here. So we have 3 cubed minus, now we plug in 1 for x here, 1 cubed, and 3 cubed is 27, minus 1 cubed is just 1, equals 26. Okay, so that's our answer there. With integration, things can get a little bit messy. So we can do one that kind of ends up in a fraction. So what if we integrate from 0 to 1 of 5x to the power of 6 dx? So this is exactly the same thing as before. Our coefficient comes with this whole thing up top. So we have 5x to the power of 6 plus 1 divided by 6 plus 1. And we want to evaluate this from 0 to 1. So just plug in, well, we can simplify this first, I guess, make it look a little bit nicer. So we have 5x, 6 plus 1 is 7, divided by 6 plus 1, which is 7. Then we will evaluate this from 0 to 1. All right, so now we will plug in 1 up top first. So 5 times 1 to the power of 7 over 7 minus 5. Now we're plugging in 0, 0, 0 to the power of 7 divided by 7. Okay, so now we just simplify this a little bit. 1 to the power of 7 is just 1. So we get 5 times 1, which is 5 over 7 minus 0 to the power of 7 is just 0. So that whole thing becomes 0 equals 5 over 7. And that is the answer we're looking for. Okay, so we're going to go ahead and try to apply this to a scenario that we might see in the course now. So I just made up this question. This isn't from any practice or anything like that, but it's going to say the x component of an electric field is E as a function of x equals negative 10x plus 50. What is the electric potential? So this is a scenario where you would potentially want to use integration. I'm going to show you actually 2 ways to solve this. One where you use integration and one where you don't. You can decide for you which one is easier for you. So before we start, let's just graph this and see what this looks like, because that might give us a bit of a better idea of where to start. So we have E as a function of x equals negative 10x plus 50. So I don't know about you all, but my favorite number to use in physics is 0 because it makes a lot of things cancel out. So let's find 2 points involving 0. So let's find E where x equals 0. So that is negative 10. We're just plugging in x 0 into this equation up here, times 0 plus 50. So negative 10 times 0 is just 0. So we are just left with 50. You could probably see that from just looking at this graph that the x or the y-intercept, sorry, is 50. We just go through that just to see it a little bit better. So this is the x-axis. This will be E as a function of x. So where x is 0, we have E of x is 50. Okay. Next, we're going to find the x-intercept. So let's see where E of x is 0. So let's say 0 equals negative 10x plus 50. You can find any 2 points you want. I'm just finding these because they're easiest for me. So if we bring this negative 10x to the other side, we get 10x equals 50. And this means that x equals 50 over 10, which is 5. Perfect. So this is basically saying where y, or e of x in this case, is 0, x is 5. So we're going to do 5. And this question should actually be saying, what is the electric potential at x equals 5? So we can see that. So we have a line that's going to look like this, just to visually show what that looks like. Okay, so now we can start solving this. We know that v as a function of x will equal negative of the integral of e of x dx. So using our new knowledge, we can just integrate this function and that will give us v of x. Since also we want to look at this at x equals 5, we want to integrate from the y-axis to this point. So here at y equals 0 and x equals 0 is more important. So we want to integrate from 0 to 5. So that's essentially a trick or rule of these problems. If it's saying x equals 5 or x equals 6 or 7, whatever number is here, you want to integrate from 0 to that number. So just keep that in mind when you're solving these questions. So that will give us the area under this curve here. All right, so we can plug in our expression there. Negative. So one important rule of integrals that I didn't mention on the previous slide is that you can take integrals separately in a sum, essentially. So you don't have to take the integral of this whole expression. You can take the integral of negative 10x and then 50 and then add them together. It just simplifies things quite a bit. So that's just how I'm going to write it now. So we have negative the integral from 0 to 5 of negative 10x dx plus the integral from 0 to 5 of 50 dx. And now it's just solving this essentially. So we will write out what doesn't change. There should be equal sign here, equals negative. So looking at this one first, we have the negative 10 that comes with us. X to the power of 1 is there now, plus 1 divided by 1 plus 1. And we want to evaluate this from 0 to 5. I'm going to just draw a little dash line here, getting a little crowded, so we know that these two are separate. Here we go, plus. Now looking here, you might not quite know what to do here, but remember, this is the same as 50 times x to the 0, because anything to the power of 0 is just 1. So these two are equivalent, which means the 50 comes with us. 50 x to the 0 plus 1 divided by 0 plus 1. And we want to evaluate that from 0 to 5. All right, I'm just going to simplify that down a little bit, make this a bit easier. So negative 10 will stay there. X, 1 plus 1 is 2, divided by 1 plus 1 is 2. And we want to evaluate that again from 0 to 5. Haven't done that yet, so that stays there. Plus 50, 0 plus 1 is 1, or x, I guess, should be there instead. So 50x times 0 plus 1, which is 1, divided by 0 plus 1, which is 1, again, evaluated from 0 to 5. So looking here, we can make a few simplifications. 10 divided by 2 is just 5. So that can stay on the top there. And 50 divided by 1 is, of course, just 50. So we can get rid of that 1 there when we go to evaluate. All right, so v of x equals negative. We need to keep remembering to bring that negative down. Try not to forget that. So we're going to plug in first this 5 into this x here. So we have negative, I'm going to put brackets around this just to keep it a little more tidy, 5. We're putting in x, which is 5 squared. So that's that first one. And then we're going to say minus, we're now going to plug in 0 up here. Negative 5 again, 0 squared. So that is that first bit. I'm going to put even more brackets around here just to make it super clear. So we did that evaluation. Now we're going to do this second evaluation here. So we have 50, we're putting in 5 for x, so that's just 5, minus 50, and we're now putting in 0 for x here. There we go. Now we just need to simplify this a little bit. So we have negative still. 5 squared is 25 times negative 5 is negative 125. So remember to keep all your negatives together. Minus 0 squared is 0. 0 times 5 is also 0. So that is still 0. Plus 50 times 5 is 250. So we have 250 minus 50 times 0 is 0. All right. So we have negative finally, negative 125 plus 250. So this equals negative 125 plus 250 is 125. And that is our answer. So this is how you would go about doing this problem with integration. If it seems kind of long and complicated, you would be right. For fairly simple equations like this, linear equations, there is a much easier way to do this. So I'm going to see how quickly I can erase all this. Okay, not too bad. So there is a graphical way to do this that works very well if you have a linear equation. But you can imagine if you had something, say, squared or cubed in there, and your graph was not a nice straight line, it would be really, really difficult to find the area under that curve. But lucky for us here, this is going to be method 2. This is just a triangle. So we know the formula for the area under the curve of a triangle. We can say that v of x equals the negative of the area under our line there. So equals negative 1/2 base times height. And that is literally just the formula for the area of a triangle. You should be able to find that online fairly easily. So v of x equals negative 1/2. Our base here, this is 0, is 5 units, so 5. And then our height here from 0 to 50 is 50. Okay, so then 5 times 50, we'll just do this step by step so that we can see how this works. 1/2 of 250. And then negative 1/2 times 250 is negative 125. So you will see that that is exactly the same answer as we got from integration, which is exactly what we want. So I would use this method if on an exam it ever asks for you to find the electric potential by integration. You can use this method to check really, really quickly. It only took us 3 lines to get there. I also can't imagine the teaching team asking you to do some crazy integral on a test that you wouldn't be able to solve an equation in this way. So if you're not familiar with integrals and you want to just learn this method, I can imagine that would be okay. Don't completely quote me on that, but maybe try to get used to this because I can imagine it would be very useful in a lot of the problems that you'll face because they shouldn't be too complicated. So I hope that this helps. If you have any questions, as always, feel free to email me. And if you have any suggestions for future videos, as always, let me know. Thanks, and I will see you next time.